This is lesson 5. We're going to talk about polar coordinates and graphs related to BC calculus, but first let's go look at a simple review from our pre-calculus days. Normally we use rectangular or a Cartesian coordinate system to graph our functions, but we can show that some problems in math are easier to analyze if we use polar coordinates. And the Cartesian plane allows us to identify a point with an XY or in three-dimensional XYZ coordinates. The equations that correspond to these graphs have either been rectangular form or parametric form. But now we're going to look at polar graphs. In polar coordinates, a point in the plane is defined by a pair of numbers r and theta. The number theta measures the angle between the positive x-axis, called the polar axis, and a ray that passes through the point. And we saw that in this image here. So the polar axis is here at the origin, and this ray is at some point. The radius is 2, and the angle is pi over 4. So you can think of a polar equation like r equals f of theta, where x, the x direction, is an angle times the cosine of the angle, and y is the radius times the sine of the angle. So in this lesson and the next lesson, we're going to explore the polar coordinate system, conversion of equations, graphs, and focus on tangent lines, arc length, and area related to calculus. So these are the information that you have probably seen in a pre-calc class, where we need to convert from polar to rectangular or from rectangular to polar. So we'll experience some of those basic features first. Let's look at this, where we want to convert the polar point 4 and 2 pi over 3. We want to convert that to a rectangular equation or a rectangular point. So x is r cosine theta, and our radius is 4, and we have cosine of our angle 2 pi over 3. And then y is r sine theta, so 4 sine of 2 pi over 3. So if you want your x coordinate, that would be 4, and the cosine of 2 pi over 3 is negative 1/2, so our x coordinate is negative 2, and our y coordinate is 4, and the sine of 2 pi over 3 is radical 3 over 2, so our y coordinate is 2 square roots of 3. So we have an x and a y coordinate for our polar point. So this is our polar point. In part B, you can turn the camera off and give it a try for yourself, and then come back to check your work. I have x as the square root of 5 times the cosine of pi over 6, and y is the square root of 5 times the sine of pi over 6, and those coordinates work out to be the square root of 15 over 2 and the square root of 5 over 2. In example 2, we're going to go backwards now. So we've got to convert the rectangular points to polar points. So converting to rectangular, we want the radius, and that would be the x squared plus the y squared. And that radius turns out to be 4. And then we want the angle theta, and theta is the angle whose tangent is 2 square roots of 3 divided by negative 2, and that angle would be 2 pi over 3. So just as we converted the example 1a, we can convert backwards for that same point, and our rectangular point converts to this r and theta. In part D, we've got the square root of 5 squared plus negative 5 squared for our radius. Excuse me. And our radius is 5 times the square root of 2. And then our angle theta is going to be the angle whose tangent is y over x. So the angle whose tangent is negative 1 would be negative pi over 4. So our r theta is 5 radical 2, and the angle negative pi over 4. Next, we're going to look at polar equations, and just like converting points from one system to another, we can also convert entire equations from one system to another. So in our first example, y equals 4, we're going to say y is r sine theta. So r sine theta is 4, which tells me r is 4 divided by sine, or 4 divided by sine can be 4 cosecant theta. So we have a straight line in rectangular form can be converted to our polar equation, r equals 4 cosecant theta, or 4 divided by sine theta. In example B, it's a little more complicated. We know y represents r sine theta, and x is represented by r cosine theta. And if we use substitution to replace those, we can isolate the r on the left-hand side and factor out that common factor of r, leaving the 2 on the right-hand side, and then dividing by that common factor, we have a polar equation, 2 divided by the difference of sine and 3 cosine theta. This is our polar equation that represents the straight line. And if you have a graphing utility, you can convert, or you can graph both of these, all 3 of these, and see that they do represent the same graph. In part C, we're going to turn y into r sine theta, and 2x squared would be 2r cosine theta quantity squared. So we have r sine theta is equal to 2r squared cosine squared theta. So we want to get rid of one of these extra r's here. So dividing through by that common factor of r, we can eliminate those factors through on both sides. And then r is going to be, sine over cosine squared. So we got sine over cosine squared with a, with a 2 down here. So r is 1/2. We have sine over cosine, so that's tangent. And then cosine on the bottom is secant. So we have r is 1/2 secant theta tangent theta if you wanted to write it as a single term. So we've converted from rectangular to polar in this example. In example 4, we'll try the other way, converting from polar to rectangular. So in this case, I want to get a representation. We'll say r divided by secant can be -3, and secant in the denominator is r cosine theta in the numerator, and r cosine theta is another name for x. So this is a vertical line through x equals -3, and we've converted polar to rectangular. In example B, I want to multiply the denominator by both sides to clear that fraction. So we're equal to 4, and then distributing r plus 2r cosine theta is equal to 4. And r cosine theta is equal to x. So we have r plus 2x if I substitute there. And then r can be represented by solving x squared plus y squared. And we have, let's subtract this. We'll get the 4. We'll say that's 4 minus 2x. And then I want to solve for y in terms of x. So how about if we square this side and then square this side? So this one is a little more complicated. That would leave us with x squared plus y squared. And then expanding this, we would have 16 minus 8 twice, so that's 16x plus 4x squared. And if we solved everything, put everything on one side and collected like terms, we would have 3x squared plus y squared plus 16x and then minus 16 equals 0. So we have some really messy polynomial function in terms of x and y in this case. And then finally for part C, we've got r times cosine theta plus 2 sine theta, and that's equal to 3. So r cosine theta plus 2r sine theta is equal to 3. And r cosine theta is another name for x, where r sine theta is another name for y. And we could stop there, or if you felt led to solve for y, you could say y is x minus 3 divided by 2. So we could say y is 1/2 of x minus 3 quantity, and solve that for our rectangular equation. Here in example 5, we want to describe what you know about the graph of each polar equation, and then convert the polar equation to a rectangular equation and sketch the curve on the graph that's provided. So I know r equals 3. To me, that just seems logical. It's going to be a circle. The radius is 3. It's centered at the origin. And the equation would be x squared plus y squared equals r squared. So that would be 9. And drawing that picture, if we could draw here with a radius of 3, we'd have this image here. And we could turn that to nice bright red possibly to show, no, we want the color of the line, not the fill color, to show that we have that circle there, centered at the origin, radius 3. So that one's pretty straightforward there. In part B, we have r equals negative 3 sine theta. So in this case, I need an r over here. So to keep the r consistent, we could square, or we could multiply through both sides by an r to keep that balanced. And r squared represent x squared plus y squared. And 3r sine theta represents negative 3y. So in this case, I would want to complete the square. So let's say we have x squared plus y squared plus 3y. So 3y, half of 3 is 1.5. 1.5 squared is 2 1/4. So we have a complete square here. But to keep that balanced, I'm going to convert it over to decimals here. To keep that balanced, I would also have to add 2 1/4 to the right side to keep the equation balanced. So this case, we have a circle. The center is located at 0 and negative 1.5. The diameter of the circle is 3. Drawing that picture, we can do this. We got a circle that whose center, it's going to be tiny here. Let's see, 1.5. So I think I've got that there. We've got a circle whose diameter is 3. It's centered at 0, negative 1.5 here. This is the center, 0 and negative 1.5. And got a diameter of 3, lives right there. Then in part C, we have r is 5 over cosine. So if we cross multiply, r cosine theta is 5, and r cosine theta is another name for x. So this is a vertical line, and it passes through the point 5, 0 at x equals 5, 0. Let's see, we need a straight line. How about that? Vertical line. Looks something like that. Passes through the point 5, 0. vertical line. And then the last thing we want to look at from pre-calc is how you can use an auxiliary graph to be able to sketch a polar curve. So consider the function y equals 1 minus the sine of 2x from 0 to 2 pi. So we have one full revolution of that function, and it's shown in the graph below. Since there's going to be unique y values on the domain, we can use the table, and that can help us to graph the graph in polar form. Consider the values for y and x as they correspond directly to the polar equation for r and theta, and then you can use that to sketch the graph of the polar equation. Let's look at the table. Here you notice our table. I took this off of the calculator. After graphing 1 minus 2 sine x, I created this table. One thing I want you to notice is where the negative r values live. So if you pay attention here, these values here, these negative r values, they're going to be the values that create the inner loop for what's going to be called a lemniscate with an inner loop. A limacon with an inner loop. So it looks like this. And in calculus, it's important to note where the positive x values on the given domain are and where the r values are negative. So the inner loop was created, let's make a note of this. The inner loop, if you look back at our table, is created where the values go from pi over 6 to 5 pi over 6. So that's what created this bit of the loop here. So you can see pi over 6 here to 5 pi over 6. They started out going this way and then around based off that table information. So anytime you have a graphing utility, you can use that as a clue, that auxiliary graph, to get key information for your polar graph. Next, let's jump over to the slope of tangent lines and polar coordinates. And in order for us to find the slope of a tangent line, we can use the parametric form for the derivative, dy dx, from our previous lesson, along with the chain rule to establish a theorem. So if we have some function y in terms of f theta, and it's a differentiable function, then the slope of the tangent line at any point r theta on the graph of r can be found by dy dx, where dy d theta is f theta cosine theta plus f prime sine theta, and dx d theta is negative f theta sine theta plus f prime theta cosine theta. And that's all true provided that the denominator is not 0 at the point that we're interested in on that polar graph. So let's give this a try here. One of the things you want to pay attention to are some of the key features and facts that you can create the functions x theta and y theta first, and then find y prime theta and x prime theta, and then divide to find your horizontal tangents, your vertical tangents, or if your dy d theta and dx d theta are both 0, then you have no conclusion, since that would be indeterminate form. And here we're going to give that a try in example 7. Okay, so in this example, we're going to do 3 things. First, we're going to create our x equation by multiplying everything by cosine. So our x of theta is going to be cosine times all of this. So cosine theta plus cosine times cosine, so cosine squared. And then we want to take the derivative based off of our information on the last chart. So that's going to be negative sine theta. Negative sine theta minus 2 cosine theta with the chain rule, so sine theta. And we have our two pieces for that. Secondly, we're going to create a y equation by multiplying everything by sine. So we're using this equation, and our y of theta, we're going to multiply everything in r by sine. So we have sine of theta plus sine times cosine. And then we want to take the derivative. So we have y prime of theta, and that's going to be cosine theta. And then we got the product rule. So this is going to be negative sine squared theta plus cosine squared theta. And then if we collect like terms, we can pull out cosine squared theta plus cosine theta. And then I'm going to rewrite the negative sine squared as 1 minus cosine squared. So we have our x theta, our x prime theta, our y theta, and our y prime theta. Now, the next thing we want to do is we want to third thing, we're going to find y prime theta divided by x prime theta. So our y prime was, oh, let's go back and look at this a minute. We can say this is, let's see, plus, minus, plus. So we got 2 cosine squared theta plus cosine theta minus 1 is our reduced down y prime theta. So we're going to use these things. So our y prime theta over our x prime theta is going to be 2 cosine squared theta plus cosine theta minus 1 divided by the x prime theta. That was negative sine theta. And then again, I'm going to factor out the sine from both terms and make that 1 plus 2 cosine theta, grabbing that information back from here. I factored out the negative sine and made that 1 plus 2 cosine theta for our x prime of theta. Now, when you look at these two, in the top one, we could use the quadratic formula right here. So I'm going to say let's use the quadratic formula. And then we would find dy d theta is that our cosine is equal to opposite b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So this is going to turn out to be, let's see, what do we got? 1 plus 8, so 9. That's going to be 3, negative 1 plus or minus 3 over 4. So we have 4 divided by 4. So our cosine theta is going to be either negative 1 or, let's see, 2/4 or 1/2 for that particular piece. And then looking for dx d theta, where dx d theta is 0. So where's that 0? That happens at theta equals 0, pi, 2 pi over 3, and 4 pi over 3, solving for all of these cases. So we want where dy d theta is going to be either plus or minus pi over 3 or pi. So let's go back and look at the graph for a minute. We have some vertical tangent lines There's one here and here. And we have horizontal, we have a vertical tangent line here, a horizontal tangent line here, and a horizontal tangent line here. So the place where we have, let's take a look at our information. So I think we don't have a conclusion at pi. That would be no conclusion. So to summarize what's going on that graph, we had vertical tangent lines. So the vertical tangent lines where dx d theta happened, that would have been 0, 2 pi over 3, and 4 pi over 3. We had horizontal tangents where dy d theta is 0, and that would happen at negative pi over 3 and positive pi over 3. And we had no conclusion if both dx and dy d theta were 0, and that would have happened at pi. So this would have been the summary for finding the points on that cardioid that had vertical or horizontal tangent lines, and then we could use a graphing calculator to verify that. In this example, if we have the function value equal to 0 or the derivative at that function value not 0, then we know that the line theta equals our a value or alpha is tangent to the pole to the graph of that polar function. So in other words, if you find the zeros of r equals f of theta, they can help you find the tangent lines at the pole. In the next example, we're going to look at a 3-leafed rose curve that has more than one tangent line at the pole. So let's take a look at that. We've got this r equals 4 sine 3 theta, and we want to find dy dx. So dy dx is 4 sine 3 theta times cosine theta plus 12 cosine 3 theta sine theta. So I'm doing what we found on our table back here. We're creating this formula and this formula. Then our dx is going to be negative 4 sine 3 theta, negative 4 sine 3 theta times sine theta plus 4 times 3, that's 12 cosine 3 theta times cosine theta, because I'm taking the derivative here. And we want to find where x prime of theta and y prime of theta. Okay, so x of theta is 4 sine 3 theta cosine theta, and y of theta was 4 sine 3 theta sine theta. So I use this x theta and this y theta to create our derivative. Now, in part B, so we've got our derivative set up. We calculated the x of theta and the y of theta. We want to calculate the slopes of the 3 tangent lines for the curve. So here's the actual curve. We want to know where dy dx, where theta equals 0, and we want to know where dy dx. So we're looking at polar curves, the polar zeros. Where are those polar zeros? So they're telling us 0 pi over 3 and 2 pi over 3. And we had 4, what was our function? 4 sine 3 theta equals 0, where the sine of 3 theta is 0. So 3 theta would be 0 plus pi times n, where n is an integer, or dividing by 3, 0 plus every pi over 3 n. And that was verified here in our original setup. So we want to look at 0 at pi over 3, and then at dy dx, where theta is 2 pi over 3. So here you can see this particular tangent line. This is where y prime is 0. This one would be where y prime is going to be square root of 3, and then this one y prime would be negative square root of 3. So in each particular case, this one is 0, this one is radical 3, and this one is negative radical 3. And just to save time, if we substitute it in here and substitute it in here, you would find those values there. Now, for the last piece, if we use a graphing utility, let's go there, to find the locations of all the horizontal tangent lines and discuss any significance of this point. So what I did was I took the graph dy d theta equals 0. That was my 4 sine 3 theta cosine theta plus 12 cosine 3 theta sine theta. So I took my dy d theta, my numerator, and set it equal to 0. And I found that theta is 0, pi over 2, and pi. Theta is about 0.65905 and about 2.4825. Okay, so using my graphing utility, let me show you what I did. I graphed the function in function mode, and I found out that I had a maximum right here at 0.659. See if I can draw my graph. Yes. So I had a maximum right here. Well, I can't draw in the graph. And then I had, this one would be at pi over 2. We changed from negative to positive, and then again from positive to negative. So this would be a maximum here at 0.659, and this would be a maximum here at 0.248. So that's what I'm showing you here on my information. So points on the curve in the XY coordinates, if we wanted to make a table, we could do that. Points on the curve in an XY coordinate system, we would have at X and Y, we had 0, 0, then we had 0.659, 0.659. The Y coordinate was, I think, 3.674. So I'd have to find that by substituting back in 3.674. And then at pi over 2, that was 1.57. So I'd substitute back into my function. That would give me -4. And then the other maximum was 2.4825. Again, that substituted to 3.674. And then substituting pi, I would get 0. So again, without spending a lot of time doing calculator steps, I would have to go back and put my function 4 sine 3 theta into the graph and then evaluate these values here. So I could do 4 sine 3 times our theta to 2.4825 to show you that I get that value 3.674 without wasting a lot of time. So in another key point is the fact that at 0, -4, I have an absolute minimum. That's an absolute minimum. And that's going to be on the tip of a leaf. If you go back and look at the graph, so back to our picture, so 0, -4. The R value maximum is going to be 4 there. You can see that R value maximum is a 4. So just further analyzing, the R value maximum is absolute value of the radius is 4. And then maybe a fourth point is we've got a horizontal tangent line, and that happened, where did those happen? Where theta was 0, and then pi over 2, and then pi, and 6.59, and 2.483, because we had a maximum, and then we started out at 0. That's a horizontal tangent line. And again, so we had this, here. Okay. I think that pretty much analyzed the entire thing. If you wanted to mark your graph up, you could mark this as 0. This is a max at 0.659. That's a max. This was pi over 2. This is another max at 2.482. This is our pi. This is another max. So we change from positive to negative. You've got a horizontal tangent line. This is a minimum, negative to positive. Then you got positive to negative, a horizontal tangent line. Okay, oh, I missed one part. So on part B, we want to find the 3 points where the R value is a maximum, and show the tangent lines perpendicular to the line segment connecting the point to the origin. So I would imagine that would be this tangent line, that tangent line, and then that tangent line. So R is a maximum where the sine of 3 theta is either plus or minus 1. So 3 theta is going to be at pi over 2, at 3 pi over 2, and at 5 pi over 2, because the maximum, 4 is the maximum petal length. So theta dividing each term by 3, we would have pi over 6, pi over 2, and 5 pi over 6. So dy dx at pi over 6, again, I'm substituting this information into my dy dx, which was back here. So I have this pre-programmed into my calculator, and you can check that I'm doing this correctly. I got the square root of 3, and that's perpendicular to the tangent at pi over 6. So that slope would be radical 3 over 3. The second one at pi over 2, dy dx, when theta is pi over 2, is going to be 0. So that's perpendicular to the tangent at pi over 2. So if we have a 0 slope, the perpendicular slope would not exist. It would be vertical. And then dy dx for our last angle was 5 pi over 6. And that calculated to be square root of 3, which would be tangent to the 5 pi over 6 angle. And again, that opposite reciprocal would be negative square root of 3 over 3. And we can show those lines here, this one, and this one, and this one. Okay? So we got all of those. So pi over 6, pi over 2, 5 pi over 6. And then part E, the very last example, we want to write the equation for the tangent line that passes through the point r theta 4 and pi over 6. So we're looking for this line. We're looking for this tangent line. We're writing that equation for that tangent line. So we got 4 cosine pi over 6 and 4 sine pi over 6. We need our x and our y. So our x value is 2 square roots of 3, and our y value is 2, so we have a point. We need a tangent line at our theta, which was pi over 6, and what did that turn out to be from the previous example? Was negative dy dx, when theta was pi over 6, was negative square root of 3. So to write the equation for a tangent line, we need to have a point and we need a slope. So our tangent line is going to be y equals negative square root of 3 x minus our x sub 1 plus our y value. So we have all of that, and that finds us at the end of lesson 5. One more lesson to go.